Hello viewers, continuing with our series on continuity and differentiability, today we are going to discuss two special techniques of differentiation, one called logarithmic differentiation and the other which would help us to differentiate functions which are in the parametric form. Let us start with looking at some functions which you may not have come across earlier as in the methods of differentiation. Let us consider functions of the kind x to the power x, cos x raised to the power x, log of x raised to the power tan x. These are special class of functions which in general can be expressed as a function of x raised to the power a function of x. So far we have not learned any method of finding derivatives of such functions. And just in case you are thinking about using the formula x to the power n to differentiate x to the power x, then stop and understand that that formula, that is the derivative of x to the power n is n x to the power n minus 1 is applicable only if n is a constant, is any real number. In this case, the power is also a function of x. So, here we use logarithm to the base e to differentiate such functions. Now, what do you know about logarithmic functions? Let us just catch up with that. Logarithmic functions are defined for any b greater than 1 as functions which are defined on positive real numbers to the real numbers, and the rule is y results in log of x to the base b if b raised to the power y is same as x. So, there is definitely a relation between exponential functions and logarithmic functions. If you had spent a little more time on this, you would have recognized that they are inverse functions of each other. Along with that, there are several useful properties of logarithm which we will be using as we progress down to this method. These are very essential and these are the key to the process which is known as the logarithmic differentiation. So, do make a note of them. Along with that, what we also need is an understanding of what are the derivatives of log and exponential functions. So, here are results which are mentioned just directly without proofs in your textbooks as well, which says that the derivative of exponential function is exponential x, derivative of log x, and when I write log x as v, that is the mathematicians do, it is meant to be with the base e. So, derivative of log x is 1 by x, derivative of a raised to the power x is a to the power x log of a, and derivative of log x to any other base other than e. So, in this case base a is same as 1 by x times log a. These four results will of course play a role as we go along and use the derivatives of logarithmic functions and exponentials anywhere else as well. Let us demonstrate to you the method, the process which is known as logarithmic differentiation through a simple problem. Starting with find dy by dx if y is equal to log of x raised to the power tan x. So, we begin of course with our function which is y is equal to log of x raised to the power tan x. In order to make it possible for us to differentiate, we take logarithm, and of course, again I am emphasizing to the base e of both sides. So, I get log of y is equal to log of log x raised to the power tan x. This gets rewritten as tan x into log of log x. How? Again, if you had noticed, this was one of the properties listed in our earlier slide. Here we have log of p to the power n is equal to n times log p. This helps us to bring the power as a factor in this expression, and therefore, we are now ready to differentiate both sides with respect to x. I get the derivative of log of y with respect to x, derivative of tan x into log of log x. This needs to be looked at with care, that when you differentiate log of y, there is a presence of chain rule, because log y is composition of logarithmic function and y which is a function of x, whereas the right hand side is product of two functions. So, to differentiate the right hand side, you need the product rule, and therefore, what would be the derivative of log y 1 by y into dy by dx, whereas the right hand side will result as the application of product rule applied on tan x and log of log x. So, we get on differentiating 1 by y dy by dx equal to sec square x log of log x plus tan x, and note how we have differentiated log of log x. Again presence of chain rule, log derivative will give me 1 by log x. So, when I say log derivative, it is derivative of log x with respect to log x, and then chain rule requires that I multiply with the derivative of log x, which is 1 by x, and thus our dy by dx is ready. Taking y to the right hand side, I get log of x raised to the power tan x into sec square x log of log x plus tan x into 1 by x log x. Not much gets simplified in this case. So, obviously, we would not worry too much about the simplification. Let us take another question, and this is one of the very frequently tested question in the class 12 board exams. The question says find the derivative, that is dy by dx, where y is x to the power sin x plus cos x raised to the power x. Now, you can see that it is just the first question that we did earlier repeated almost twice, because both the terms are of the class where we have f of x raised to the power g of x. So, both the functions need log in order to get the differentiation done. But also remember that there is no rule which says that log of the sum is same as sum of the logs. So, what can one do? Simply start with u as x raised to the power sin x and v as cos of x raised to power x. Then your y becomes u plus v and dy by dx is du by dx plus dv by dx. That is exactly what we did in our previous question. So, I will leave this for you to complete yourself, repeat the same process mechanically and you will be fine. Consider another application. Find dy by dx if y is equal to this big expression where we have a square root, I have a quotient and I have product in both numerator and denominator. A usual chain quotient product rule procedure will make the task quite tedious. So, this is another situation where we take help of log and its properties which help us rewrite this function, simplify it down and then we bring in differentiation. Starting with y, which is square root of x plus 1 into x minus 3 upon x minus 4 into 7 minus x into x plus 2. Taking log of both sides, we get log of y as log of the entire expression, and again using the properties that we have just displayed, it all simplifies to half of log of x plus 1 plus log x minus 3 and then minus, because now we are looking at log of m by n resulting in log m minus log n. So, the entire expression gets written either as the sum or difference of terms which are with log. Taking the derivative, I get 1 by y dy by dx is equal to half times of 1 by x plus 1 plus 1 by x minus 3 minus 1 by x minus 4 plus 1 by 7 minus x. Now, where did I get this plus from? Because I had log of 7 minus x. So, when I take the derivative, it will be 1 by 7 minus x into the coefficient of x, which is minus 1, and therefore, I get a positive sign there, minus 1 by x plus 2 as the derivative of log x minus 2, and your problem is done. You just have to now rewrite your dy by dx by transposing y to the other side and just complete by saying what that y was. So, this is one more application of using the log to find the derivative of a function, process known as logarithmic differentiation. Let us also consider something new which you have again not come across earlier, functions which are in the parametric form. The functions which are in parametric form represents the equation of a curve by a pair of equations, where these pair of equation represents the coordinates of the point on the curve in terms of a certain parameter. In this case, for example, if I have x as cos t, y is equal to sin t, this represents nothing but parametric equation of a circle with radius 1. You do not believe that? Well, it is so. You are familiar definitely with x square plus y square equal to 1 as the Cartesian equation of a circle with unit radius. So, if you do square x and y and add, cos square t plus sin square t is equal to 1. So, t changes and it generates the coordinates of the points which lie on the curve, and that is a way of representing a Cartesian equation in terms of parameter. We are interested in finding the derivative of y with respect to x, where both x and y are functions of a certain parameter, say t. Then in that case, dy by dx is nothing but dy by dt divided by derivative of x with respect to t. So, as t changes, we find the instantaneous rate of change of y and divide by the instantaneous rate of change of x, provided denominator is not 0. And we are fine to find then the derivatives of functions which are in the parametric form. Consider one application. If x and y are connected parametrically by the equations, x is a times theta minus sin theta, y is a times 1 plus cos theta. Find dy by dx. So, what do? You begin by first finding dx by d theta. So, derivative of a times theta minus sin theta is nothing but a times 1 minus cos theta. Similarly, derivative of y, you have practiced differentiation to a large extent right by now. So, you are expert at finding such derivatives. dy by dx is nothing but the quotient of these two derivatives in the order derivative y with respect to theta divided by derivative of x with respect to theta. One does expect you to simplify this expression a little more. In this case, a gets cancelled. Not only that, trigonometric identities help us to rewrite sin theta as 2 sin theta by 2 cos theta by 2, 1 minus cos theta as 2 sin square theta by 2. It all simplifies to be same as minus of cot theta by 2. That would be the derivative of y with respect to x, where x and y are parametric functions of theta. So, the derivative is also a function of theta, it is not the function of x in this case. So, today's lesson covered two interesting important techniques, one logarithmic differentiation and the other which just touched upon the derivatives of functions in parametric form. I hope this has helped you to clear your doubts. Now, it is up to you to open books, start practicing and get expert at both the methods. See you in our next lesson. Thank you.